This section 4.4 is titled Optimization 1. To optimize means to get the best of something. You want the best. And that could mean you need a maximum, or it could be that you need a minimum. For example, you want to maximize profit, but you want to minimize the cost. So either a max or a min is going to give you the optimized value. Okay, now typically speaking, we look for absolute max or min in this section, and that's different from relative max and min that we had seen before. So what is absolute max, absolute min versus relative max and min? As the word indicates, absolute meaning there's nothing else that's bigger or nothing else that's lower than that value. So let's take a look at a graph. On this interval from A to B, suppose the graph has this shape. It's going back here. So these points are turning points. Okay, there's turning points right here. Let's label this A, B, C, D, E. Okay. Now, B in its location, in its relative neighborhood, is a maximum. However, D is higher than it, and there's no points that go higher than D. So D is your absolute maximum. E in its neighborhood is a minimum. However, C is the relative min, and E is lower than it. So E in this interval from A to B is your absolute minimum. Okay, so B is a relative max, C is a relative min. Also by default, in this neighborhood, that's a relative max, but being an absolute max is even stronger. A also is relatively low as an endpoint. Now the goal in this section is to be able to find not the relative max and min. This was done in sections 4.2, 4.1, and 4.3. Our goal is to figure out how to find absolute max and min, and we'll be doing so in the case of a closed interval. So what I mean by closed interval is the interval A to B on the x-axis. That's the closed interval when we're trying to find absolute extrema or extrema. That's absolute max and min, max and min on a closed interval AB. Now what we know is that if a function is continuous, okay, this is actually theorem 3 in our textbook. I'm going to just quickly stop here for a second and show you the text. On page 305, where this section begins, I need to dim the screen so you can see this better. This is where optimization starts, and there's a graph here that shows you how you have an absolute max there, absolute min there. There's some relative maximums and so on, but the absolute is the lowest point of all. Okay, so cancel that zoom. Going to the next page, maybe I need to brighten it up a little bit. There's some graphs here that show you how like x squared goes on forever. It has no absolute max because it keeps going up, but there's an absolute minimum there. But if you were to use a closed interval, you'll be able to find both at max and min. And that leads rise to the next topic, absolute extrema on a closed interval. So if you have a closed interval, the graphs stop at those points. Then if the function is continuous, remember the word continuous from chapter 2, then you'll be able to guarantee an absolute minimum and an absolute maximum. Okay, so this is the theorem that summarizes what I just said. This is theorem 3 in our text. It says that if a function is continuous on a closed interval AB, then f has both an absolute maximum and an absolute minimum value on AB, the closed interval AB. And there's a picture describing that, similar to what I had drawn before. Alright, so let's put that into our own words. Theorem 3, the absolute value theorem, says that if f of x is continuous on a closed interval AB, then f has both an absolute max and absolute minimum on AB. How do we find it? Well, let's draw a picture of what this could be. But this is the starting point A, and let's say that is the ending point B. Then notice that these are the turning points. This is when f prime is 0, first derivative is 0 because you have horizontal tangent lines. And we get that by finding the first derivative. It gives us our critical points. And then, so there's relative min, possibly absolute min here, but it could also happen at the endpoints. So to summarize this section, to be able to find the absolute max and min, to find absolute max and min, step 1, find all critical points on the interval AB. Okay, remember by setting the first derivative to equal 0, or see where it does not exist, but remember it needs to be in this interval, it needs to be defined. Next, if you just plug in all the critical points and endpoints meaning A and B, into the original function f of x, that is, the largest y value that's your absolute maximum. The smallest y value of all is the absolute minimum. Okay, so we're going to use these steps and try the worksheet that I have for this section and put our knowledge to work here. So I'm going to keep this here for a second as we do the first problem. This is the worksheet you're looking at. Find the absolute, that's a key word, absolute extrema, meaning max and min, of this function on that closed interval, -1 to 2. So this is our interval from A to B. So the first step is find all critical points on that interval. So step 1, find f prime and set it to equal 0. This is a nice polynomial, easy to differentiate. 12x cubed minus 12x squared. To find the critical points, I'm going to first factor 12x squared, and I have x minus 1. If I set this to equal 0, then I have two factors. This yields x to be 0, and this gives us x to be 1. So those are my two critical points. And then stop and check and make sure both 0 and 1 are within that interval. They both are. So we can move on to step 2. Okay, and in step 2 you plug in all the critical points and endpoints into the original function. I like to make a little table. So you have x and f of x. Start off with the left endpoint, -1, then 0, and then 1, and then 2. That's the other endpoint. This is your A, this is your B, this is your critical point, this is a critical point. Okay, so that's how I got these 4 values, and we're going to plug them into the original function, which is right here. Okay, just to make our job a little easy, you can go and type in y into your calculator and go to the table, and I'm going to delete all this old stuff. I have -1, 0, alright, -1, 0, 1, whoops, 1, and 2. And these are the y values. I'm going to copy them down, 7, 0, negative 1 and 60. Going back to our steps, after you plug in all the critical points and the endpoints into the original function, the largest y value, which is 16, is the absolute max, is 16, and the smallest y value is your absolute min. So this is your smallest y value. Absolute min is negative 1. Notice how I've only got the y values here. You have to read the question, and based on the question you might either leave just the y value, or you may have to write it as 2 comma 16, which tells you the location where it happens, the x, and that's the maximum value itself. So reading the homework question might be a bit of a challenge. Make sure you read it carefully. And there it's 1 comma negative 1. Alright, let's try the next problem. Here we have another polynomial. So step 1, f prime of x is 6x squared minus 6. Factor out the 6. You have x squared minus 1, which factors further difference of squares, so it's a x plus 1, x minus 1. And when I set this to equal 0, 6 is never 0. This factor gives us negative 1, and that factor gives us positive 1. So those are our two critical points. But if you look at the interval, going from 0 to 2, a is 0, b is 2, negative 1 is not valid in the interval. It's not valid on the interval AB that's given to us, so we'll only need to use x equals 1. That takes us to step 2, where we build a table, x, f of x, start with the left end point, 0, put in the critical point and then the right end point, substitute all these values into the original function. These numbers are small enough. When you plug in 0 you get 3, plug in 1, that's 2 minus 6, negative 4, plus 3 is negative 1, 2 cubed is 8, times 2 is 16, 16 minus 12 is 4, plus 3 is 7, but feel free to use your calculator if needed. So there's our absolute max. Absolute max is 7, or you may have to do 2 comma 7 depending upon the question, the way it's worded. Absolute minimum, the lowest point, happens at negative. It's at 1, negative 1. Alright, so let's move on. One more question, one last one, and hopefully you can try the homework and it'll not be too bad. So in this question, it's not a polynomial because you have x in the bottom. So before I do anything, I'm going to bring that up as x to the negative 1. Now we'll do step 1. Find the derivative. F prime of x is 9. When the negative comes down, it's positive, x to the negative 2. But now I need to rewrite this as 9 plus 1 over x to the positive 2. I'm going to set this to equal 0. To solve this equation, we can move the 9 over. 1 over x squared is negative 9. And we can multiply x squared to both sides. And you get that to go away. 1 is negative 9x squared, or x squared is negative 1 divided by 9. And when you go to take square roots of both sides, that is not real. Negative 1/9 under the square root is imaginary. All that work to say there's no critical points. So we'll move on to step 2. So step 2 was build a table and plug in the endpoints and the critical points. We don't have any critical points. That's okay. We'll just plug in the endpoints, 1 and 3. Plug in 1 for x, and you should get 8. Plug in 3. 9 times 3 is 27 minus 1/3. If you do the math there, you should get 80 over 3. Okay, so 27 times 3 is 81, minus 1 is 80, a little fraction calculation there. So which one is higher? If you divide 80 by 3, it's almost 27, so this should be your max. So absolute max, oops, can't see that, absolute max is 80 over 3, absolute minimum is 8. I'm going to go back and check all of these problems on our graphing calculator. So the first question, if you go to y equals and type that in, it should look like this. Now if you push graph on a standard window, it shows us the nth polynomial that goes on for a while, but we're looking only from -1 to 2. So you can go change your window. On the x, you just want to go from -1 to 2. Now I'm going to push trace. I'm going to type in well, what I notice here though is that I don't see what happens to these values. I need to go up higher on the y-axis. So y max, I'm going to make it 20. We kind of knew that from here. Our maximum was 16. So I push trace and type in 2. It takes me to 16. That was the max. If you look down here, the min is somewhere here, because then after that it goes back up. So push trace, type in 1. We had 1 here, and that is the low point. Let's do the second question. I'm going to type in that equation. It's 2x cubed minus 6x plus 3, and the window goes from 0 to 2 only. And looking at these values, we don't really need to go that high. -10 to 10 will be plenty for the y. And there's the graph for that over that interval. We have 7 when x is 2, so press when x is 2, that is your high point, maximum is 7, type in 1, and that's your absolute min. The last question is 9x, clear that first, 9x minus 1 over x. The window goes from 1 to 3. Let's see if our graph is going to show up. Nope, that window we had wasn't big enough. So for the y-axis, we need to go up a bit higher. So the absolute max for this problem was 80 over 3, which is in the upper 20s. So let's go up to 30 and make the scale 3. And the x values were 1 and 3. We should maybe just go with 1 and 3 because that was our interval. Alright, so the part that's captured on this interval almost looks like a line. And you see the min is down here, the max is up there, which is what we got. The minimum was at 1. Whoops, got to first push trace, then type in 1, and get 8. That was our min. And then type in 3. Max is 26.6. Repeating, that was that value. Okay, so give this homework a try, and as always, email me if you have any questions.